Question 21 reads, consider a pure sample of radioactive isotope with a mass number of 48. If the sample has a mass of 25 micrograms and the isotope has a half-life of 13.5 times 10 to the 6 years, determine the decay rate for the sample in seconds, up to 3 significant figures. So what we need to do basically is make a very large conversion from 48 AMU all the way to micrograms per nuclei. So to do that, what we're going to start out with is the 48 AMU, obviously, and then we're going to multiply, we're going to convert the AMU to kilograms, and on your formula sheet there's a number or a value of the amount of kilograms per AMU. So that is 48 AMU times, I'm sorry about that, times 1.66 times 10 to the negative 27 kilograms per AMU. And so we can cancel our AMUs here, and then so this will give us a value for the amount of kilograms present in the nuclei. But we don't want kilograms, we want to convert it to micrograms. So what we're going to do is we're going to multiply it by 1 times 10 to the 9 micrograms per kilogram. And we know that there, and if this doesn't make any sense, we know that there are 10 to the 6 micrograms per gram. So by that logic we can say there are 10 to the 9 micrograms per kilogram. Because to get from grams to kilograms we need to multiply by 10 to the third. So here's our final conversion that we're going to make, because now we have it in, once we multiply these values across, we'll have our answer for micrograms per nuclei, and this will give us 7.97 times 10 to the negative 17 micrograms per nuclei. And so this is only the first step, because now what we need to do is we need to use the equation to solve to get the decay constant, and you'll see that in just a second. So we have decay constant is equal to natural log of 2 over our half-life, but we're going to want to convert our half-life to seconds from years. And so we're going to do ln of 2 over our half-life in years, 5 times 10 to the 6 years, times 365 days, times 24 hours in a day, and then times 60 minutes, times 60 seconds. And then so what we'll be left with is natural log of 2 over 4.26 times 10 to the 14th power seconds. And then so this will give us a value for our decay constant that is equal to 1.63 times 10 to the negative 15 seconds. The inverse of seconds. And then so once we have both of these values, the micrograms per nuclei and the decay constant, we can find our rate, which is decays per second, by using R is equal to decay constant times N. And N is the number of nuclei. So this is equal to 1.63 times 10 to the negative 15 times our number for per nuclei, which is 3 point, I'm sorry, actually, so what we need to do, we forgot to consider the mass of the 25 micrograms. So if we have 7.97 times 10 to the negative 17 micrograms per nuclei, then we need to set up a proportion to solve for the number of nuclei that's in a 25 microgram sample. And then so to do that, what we need to do is we'll put 1 nuclei over 7.97 times 10 to the negative 17 micrograms is equal to 25 micrograms. And then so this will give us a value for nuclei that is 3.14 times 10 to the 17. So I'll color this in red here, and this is going to go here. And then so once we multiply across here, we'll get a value for our rate, which will be 511 decays per second. So the answer for number 21 is B.